Let's go. Alright. Let's read some stuff. Okay. Alright. We stopped at page 169 in the middle of chapter 7. And I plan to read both chapters 7 and 8 today. Yes, sir. Alright, let's get right to it. This is right after the break on page 169, so right after where we stopped. George Uhlenbeck, 24, had enjoyed his time in Rome as a private tutor to the son of the Dutch ambassador. He had secured the position in September 1922 after having gained the equivalent of a bachelor's degree in physics from Leiden University. No longer wishing to be a financial burden to his parents, it was the perfect opportunity for Uhlenbeck to be self-sufficient as he worked towards his master's degree. With no formal lectures to attend, he learned most of what he needed from books, with only the summer back at the university. Unsure whether to pursue a doctorate when he returned to Leiden in June 1925, Uhlenbeck went to see Paul Ehrenfest, who had succeeded Heinrich Lorentz as professor of physics in 1912 after Einstein chose Zurich. Sorry. Ehrenfest, born in Vienna in 1880, had been a student of the great Boltzmann. Together with his Russian wife Tatiana, who was a mathematician, Ehrenfest had produced a series of important papers in statistical mechanics as he eked out a living as a physicist in Vienna, Göttingen, and St. Petersburg. Over the 20 years as Lorentz's successor, Ehrenfest established Leiden as a center of theoretical physics and in the process became one of the most respected figures in the field. He was renowned for his ability to clarify different areas of physics, rather than for any original theories of his own. His friend Einstein later described Ehrenfest as the best teacher in our profession, and one passionately preoccupied with the development and destiny of men, especially his students. It was this concern for his students that led Ehrenfest to offer the wavering Uhlenbeck a 2-year post as an assistant while he set about getting a doctorate. The offer proved irresistible. Ehrenfest, who ensured whenever possible that his trainee physicians worked together in pairs, introduced him to another graduate student, Samuel Goldschmidt. A year and a half younger than Uhlenbeck, Goldschmidt had already published well-received papers on atomic spectra. He had arrived in Leiden in 1919, not long after Uhlenbeck, who called Goldschmidt's first paper at only 18 a most presumptuous display of self-confidence, but highly creditable. Given his doubts, a clearly talented younger collaborator might have intimidated others, but not Uhlenbeck. Physics, Goldschmidt said towards the end of his life, was not a profession but a calling, like creative poetry, music composition, or painting. However, he had chosen physics simply because he had enjoyed science and mathematics at school. It was Ehrenfest who kindled a real passion for physics in the teenager, as he set him tasks related to analyzing and finding order in the fine structure of atomic spectra. While he was not the most studious, Goldschmidt possessed an uncanny skill at making sense out of empirical data. By the time Uhlenbeck had returned to Leiden from his time in Rome, Goldschmidt was spending 3 days a week in Amsterdam working in Peter Siemens' spectroscopy laboratory. The trouble with you is I don't know what to ask. All you know is spectral lines, Ehrenfest complained as he fretted about setting Goldschmidt a much-delayed exam. Despite concerns that his flair for spectroscopy was having a detrimental impact on his all-round development as a physicist, Ehrenfest asked Goldschmidt to teach Uhlenbeck the theory of atomic spectra. After Uhlenbeck was brought up to date on the latest developments, Ehrenfest wanted the pair to work on the alkali doublet lines, the splitting of spectral lines due to an external magnetic field. He knew nothing. He asked all those questions which I never asked, said Goldschmidt. Whatever his shortcomings, Uhlenbeck had a thorough knowledge of classical physics that led him to pose intelligent questions that challenged Goldschmidt's understanding. It was an inspired piece of painting by Ehrenfest that ensured that each would learn from the other. Throughout the summer of 1925, Goldschmidt taught Uhlenbeck everything he knew about spectral lines. Then one day, they discussed the exclusion principle, which Goldschmidt thought was no more than another ad hoc rule that brought a little more order to the unholy mess of atomic spectra. However, Uhlenbeck immediately hit upon an idea that Pauli had already dismissed. An electron could move up and down, back and forth, and side to side. Each of these different ways of moving physics called a degree of freedom. Since each quantum number corresponds to a degree of freedom of the electron, Uhlenbeck believed that Pauli's new quantum number must mean that the electron had an additional degree of freedom. To Uhlenbeck, a fourth quantum number implied the electron must be rotating. However, spin in classical physics is a rotational motion in 3 dimensions, so if electrons spin in the same way, like the Earth about its axis, there was no need for a fourth number. Pauli argued that his new quantum number referred to something which cannot be described from the classical point of view. In classical physics, angular momentum, everyday spin, can point in any direction. What Uhlenbeck was proposing was quantum spin, two-valued spin, spin up or spin down. He pictured these two possible spin states as an electron spinning either clockwise or anti-clockwise around a vertical axis as it orbits the atomic nucleus. As it did so, the electron would generate its own magnetic field and act like a subatomic bar magnet. The electron can line up either in the same or in the opposite direction as an external magnetic field. Initially, it was believed that any allowed electron orbit could accommodate a pair of electrons provided that one had spin up and the other had spin down. However, those two spin directions have very similar but not identical energies, resulting in the two slightly different energy levels that gave rise to the alkali doublet lines, two closely spaced lines in the spectra instead of one. Uhlenbeck and Goldschmidt showed that electron spin could be either plus or minus half, values that satisfied Pauli's restrictions for the fourth quantum number to be two-valued. By the middle of October, Uhlenbeck and Goldschmidt had already written a one-page paper and showed it to Ehrenfest. He suggested that the normal alphabetical order of names be reversed. Since Goldschmidt had already published several well-received papers on atomic spectra, Ehrenfest was concerned that readers would think that Uhlenbeck was the junior partner. Goldschmidt agreed, as it was Uhlenbeck who had thought of spin. But as to the soundness of the concept itself, Ehrenfest was unsure. He wrote to Lorentz asking for his judgment and advice on a very witty idea. Although 72, retired and living in Haarlem, Lorentz still traveled to Leiden once a week to teach. Uhlenbeck and Goldschmidt met him one Monday morning after his lecture. Lorentz was not discouraging, said Uhlenbeck. He was a little bit reticent, and said that it was interesting and that he would think about it. A week or two later, Uhlenbeck went back to receive Lorentz's verdict and was given a stack of papers full of calculations in support of an objection to the very notion of spin. A point on the surface of a spinning electron, Lorentz pointed out, would move faster than the speed of light, something forbidden by Einstein's special theory of relativity. Then another problem was discovered. The separation of the alkali doublet spectral lines, predicted using electron spin, was twice the measured value. Uhlenbeck asked Ehrenfest not to submit the paper. It was too late. He had already sent it to a journal. You are both young enough to be able to afford the stupidity, Ehrenfest reassured him. When the paper was published in 20th of November, Bohr was deeply skeptical. The following month, he traveled to Leiden to participate in the celebrations to mark the 50th anniversary of Lorentz receiving his doctorate. As his train pulled into Hamburg, Pauli was waiting on the platform to ask Bohr what he thought about electron spin. "The concept was very interesting," said Bohr. His well-worn put-down meant he believed that electron spin was flawed. How, he asked, could an electron moving in the electric field of the positively charged nucleus experience the magnetic field necessary for producing the fine structure? When he arrived at Leiden, two men impatient to know his views on spin met Bohr at the station: Einstein and Ehrenfest. Bohr outlined his objection about the magnetic field and was amazed when Ehrenfest said that Einstein had already resolved the problem by invoking relativity. Einstein's explanation, Bohr admitted later, was a complete revelation. He now felt confident that any remaining problems surrounding electron spin would all sooner rather than later be overcome. Lorentz's objection was based on classical physics, of which he was a master. However, electron spin was a quantum concept, so this particular problem was not as serious as it first appeared. The British physicist Llewellyn Thomas solved this second. He showed that an error in the calculation of the relative motion of the electron in its orbit around the nucleus was responsible for the extra factor of 2 in the separation of the doublet lines. "I have never since faltered in my conviction that we are at the end of our sorrows," Bohr wrote in March 1926. On the return leg of his trip, Bohr met more physicists eager to hear what he had to say about quantum spin. When his train stopped at Göttingen, Werner Heisenberg, who just a few months earlier had finished his stint as Bohr's assistant, and Pascual Jordan were waiting at the station. Electron spin, he told them, was a great advance. He then traveled to Berlin to attend the 25th anniversary celebrations of Planck's famous lecture to the German Physical Society in December 1900 that was the official birthday of the quantum. Pauli lay in wait at the station, having traveled from Hamburg to quiz the Dane once again. As he feared, Bohr had changed his mind and was now the prophet of electron spin. Unmoved by his initial attempts to convert him, Pauli called quantum spin a new Copenhagen heresy. A year earlier, he had dismissed the idea of quantum spin when the 21-year-old German-American Ralph Kronig had first proposed it. On a 2-year odyssey around some of Europe's leading centers of physics, after gaining his PhD at Columbia University, Kronig arrived at Tübingen on the 9th of January 1925, prior to spending the next 10 months at Bohr's Institute. Interested in the anomalous Zeeman effect, Kronig was excited when his host, Alfred Landé, had told him that Pauli was expected the following day. He was coming to talk to Landé about the exclusion principle before submitting his paper for publication. Having studied under Sommerfeld and later serving as Bohr's assistant in Frankfurt, Landé was highly regarded by Pauli. Landé showed Kronig a letter Pauli had written to him the previous November. In the course of his life, Pauli wrote thousands of letters. As his reputation grew and the number of correspondents increased, his letters were highly prized and passed around and studied. For Bohr, who saw past the sarcastic wit, a letter from Pauli was an event. He would slip it into his jacket pocket and carry it around for days, showing it to anyone remotely interested in whatever problem or idea Pauli was dissecting. Under the cover of drafting a reply, Pauli would conduct an imaginary dialogue as though Pauli were seated in front of him smoking his pipe. Probably all of us are afraid of Pauli, but then again, we are not so afraid of him that we dare not admit it, he once playfully declared. Kronig later recalled that as he read Pauli's letter to Landé, his curiosity was aroused. Pauli had outlined the need to label every electron inside of an atom with a unique set of 4 quantum numbers and its consequences. Immediately, Kronig began thinking about the possible physical interpretation of the 4th quantum number and came up with the idea of an electron rotating about its axis. He was quick to appreciate the difficulties attached to such a spinning electron. However, finding it a fascinating idea, Kronig spent the rest of the day developing the theory and doing the mathematics. He had worked out much of what Uhlenbeck and Goldschmidt would announce in November. When he explained his findings to Landé, both men were impatient for Pauli to arrive and give his seal of approval. Kronig was taken aback when Pauli ridiculed the notion of electron spin. That is surely quite a clever idea, but nature is not like that. So fervent had Pauli been in rejecting the proposal, Landais tried to soften the blow. Yes, if Pauli says so, then it is not like that. Dejected, Kronig abandoned the idea. Unable to contain his anger, when electron spin was quickly embraced, in March 1926, Kronig wrote to Bohr's assistant Hendrik Kramers. He reminded Kramers that he had been the first to suggest electron spin had not published because of Pauli's derisive reaction. In future, I shall trust my own judgment more and that of others less, he lamented, having learned the lesson too late. Disturbed by Kronig's letter, Kramers showed it to Bohr. No doubt remembering his own dismissal of electron spin when Kronig had discussed it with him and others during his stay in Copenhagen, Bohr wrote to express his consternation and deep regret. I should not have mentioned the matter at all if it were not to take a fling at the physicists of the preaching variety, who are always so damned sure of and inflated with the correctness of their own opinion, replied Kronig. Despite being robbed, Kronig was sensitive enough to ask Bohr not to mention the whole sorry affair in public, since Goldschmidt and Uhlenbeck would hardly be happy about it. He knew they were entirely blameless. However, both Goldschmidt and Uhlenbeck became aware of what had happened. Uhlenberg later openly acknowledged that he and Goldschmidt were clearly not the first to propose a quantized rotation of the electron, and there is no doubt that Ralph Kronig anticipated what certainly was the main point of ideas in the spring of 1925, and that he was discouraged mainly by Pauli from publishing his results. It was proof, a physicist told Goldschmidt, that the infallibility of the deity does not extend to his self-styled vicar on earth. In private, Bohr believed that Kronig was a fool. If he was convinced of the correctness of his idea, then he should have published it no matter what others thought. Publish or perish is a rule not to be forgotten in science. In his heart, Kronig must have reached a similar conclusion. His initial outburst of bitterness towards Pauli amid the disappointment of missing out on electron spin had dissipated by the end of 1927. At only 28, Pauli was appointed professor of theoretical physics at the ETH in Zurich. He asked Kronig, who was once again in Copenhagen, to become his assistant. Every time I say something, contradict me with detailed arguments, Pauli wrote to Kronig after he accepted the offer. By March 1926, the problems that had led Pauli to reject electron spin had all been resolved. Now there is nothing else I can do than to capitulate completely, he wrote to Bohr. Years later, most physicists assumed that Goldschmidt and Uhlenbeck had received the Nobel Prize. After all, electron spin was one of the seminal ideas of 20th century physics, an entirely new quantum concept. But the Pauli-Kronig affair meant that the Nobel Committee shied away from giving them the prestigious award. Pauli always felt guilty for discouraging Kronig, just as he had received the Nobel Prize in 1925 for the discovery of the exclusion principle, while the Dutchmen were denied. I was so stupid when I was young, he said later. On the 7th of July 1927, Uhlenbeck and Goldschmidt received their doctorates within an hour of each other. Flouting convention, the ever-thoughtful Ehrenfest had arranged it that way. He also secured both of them jobs at the University of Michigan. With few positions then available, Goldschmidt said towards the end of his life, the post in America was for me a far more significant award than the Nobel Prize. Goldschmidt and Uhlenbeck provided the first concrete evidence that existing quantum theory had received the limits of its applicability. Theories could no longer use classical physics to gain a foothold before quantizing a piece of existing physics, because there was no classical counterpart to the quantum concept of electron spin. The discoveries of Pauli and the Dutch spin doctors brought to a close the achievements of the old quantum theory. There was a sense of crisis. The state of physics was, from a methodological point of view, a lamentable hodgepodge of hypotheses, principles, theorems, and computational recipes, rather than logical, consistent theory. progress was often based on artful guessing and intuition rather than scientific reasoning. Physics is at the moment very muddled. In any case, for me it is too complicated, and I wish I were a film comedian or something of that sort and had never known anything and had never heard anything about physics, wrote Pauli in May 1925, some 6 months after discovering the exclusion principle. Now I do hope nevertheless that Bohr will save us with a new idea. I beg him to do so urgently, and convey to him my greetings and many thanks for all his kindness and patience towards me. However, Bohr had no answers to our present theoretical troubles. That spring, it seemed that only a quantum magician could conjure up the yearned-for new quantum theory, quantum mechanics. Let me just see how long the next chapter is. "23 fucking pages. Oh my god. Okay. We can do this. Okay. Alright, time to destroy my throat again. Here's Chapter 8. The Quantum Magician. On a quantum theoretical reinterpretation of kinematics and mechanical relations was the paper that everyone had been waiting for and some had hoped to write. The editor of the Zeitschrift für Physik received it on 29th of July 1925. In the preamble that scientists call an abstract, the author boldly stated his ambitious plan to establish a basis for theoretical quantum mechanics founded exclusively on relationships between quantities which, in principle, are observable. Some 15 pages later, his goal achieved, Werner Heisenberg had laid the foundations for the physics of the future. Who was this young German wunderkind, and how had he succeeded when all others had failed? Werner Karl Heisenberg was born on the 5th of December 1901 in Würzburg, Germany. He was 8 when his father was appointed to the country's only professorship of Byzantine philology at Munich University, and the family moved to the Bavarian capital. For Heisenberg and his brother Erwin, almost 2 years older, home became a spacious apartment in the fashionable suburb of Schwabing, at the northern outskirts of the city. They attended the prestigious Maximilians Gymnasium, where Max Planck had been a student 40 years earlier. It was also the school where their grandfather was now in charge. If the staff were tempted to treat the headmaster's grandsons more leniently than other pupils, then they quickly discovered there was no need. He has an eye for what is essential and never gets lost in details, Werner's first-year teacher reported. His thought processes in grammar and mathematics operate rapidly and usually without mistakes. August Heisenberg's father, forever the teacher, devised all manner of intellectual games for Werner and Erwin. In particular, he always encouraged mathematical games and problem solving. Pitting one brother against the other as they raced to solve them, it was evident that Werner was the more mathematically talented. Around the age of 12, he started learning calculus, and asked his father to get him maths books from the university library. Seeing this as an opportunity to improve his son's grasp of language, he started supplying him with books written in Greek and Latin. It was the beginning of Werner's fascination and the work of the Greek philosophers. Then came the First World War and the end of Heisenberg's comfortable and secure world. The end of the war brought in its wake political and economic chaos throughout Germany, but few places experienced this more intensely than Munich and Bavaria. On the 7th of April 1919, radical socialists declared Bavaria a Soviet republic. As they waited for troops sent by Berlin to arrive and restore the deposed government, those opposed to the revolutionaries organized themselves into military-style companies. Heisenberg and some friends joined one of these. His duties were largely confined to writing reports and running errands. Our adventures were over after a few weeks, Heisenberg recalled later. Then the shooting died down and military service became increasingly monotonous. By the end of the first week in May, the Soviet Republic had been ruthlessly crushed, leaving over 1,000 dead. The harsh post-war reality led young middle-class teenagers like Heisenberg who embraced the romantic ideals of an earlier age, as they flocked to join youth organizations such as the Pathfinders, the German equivalent of the Boy Scouts. Others, wanting more independence, set up their own groups and clubs. Heisenberg led one such group formed by younger pupils at his school. Gruppe Heisenberg, as they styled themselves, went hiking and camping in the Bavarian countryside and discussed the new world their generation would create. In the summer of 1920, after graduating from the gymnasium with such ease that he won a prestigious scholarship, Heisenberg wanted to study mathematics at Munich University. When a disastrous interview ended any chance of doing so, a despondent Heisenberg sought his father for advice. He made an appointment for his son to see an old friend, Arnold Sommerfeld. Although the small, squat man with his martial dark mustache looked rather austere, Heisenberg did not feel intimidated. He sensed that despite his appearance, he was a man with genuine concern for young people. August Heisenberg had already told Sommerfeld that his son was particularly interested in relativity and atomic physics. "You are much too demanding," he told Werner. "You can't possibly start with the most difficult part and hope that the rest will automatically fall into your lap." Always eager to encourage and recruit raw talent to mold, he softened. "It may be that you know something. It may be that you know nothing. We shall see." Sommerfeld allowed the 18-year-old to attend a research seminar intended for more advanced students. Heisenberg was lucky. Together with Bohr's Institute in Copenhagen and Born's group in Göttingen, Sommerfeld's institute would form the golden triangle of quantum research in the years to come. When Heisenberg attended his first seminar, he spotted a dark-haired student with a somewhat secretive face in the third row. It was Wolfgang Pauli. Sommerfeld had already introduced him to the portly Viennese during a tour around the institute on his first visit. The professor had been quick to tell Heisenberg, once Pauli was out of earshot, that he considered the boy to be his most talented student. Recalling Sommerfeld's advice that he could learn a great deal from him, Heisenberg sat down next to Pauli. "Doesn't he look like the typical hussar officer?" whispered Pauli as Sommerfeld entered. It was the beginning of a lifelong professional relationship that never quite blossomed into a closer personal relationship. Personal. They were simply too difficult. Heisenberg was quieter, friendlier, less outspoken and critical than Pauli. He romanticized nature and loved nothing more than hiking and camping with his friends. Pauli was drawn to cabarets, taverns, and cafes. Heisenberg had done half a day's work, while Pauli still slept soundly in his bed. Yet Pauli exerted a strong influence on Heisenberg and never passed up a chance to tell him, with tongue-in-cheek, you are a complete fool." In the middle of writing his dazzling review of relativity, it was Pauli who steered Heisenberg away from Einstein's theory and towards the quantum atom as a more fertile area of research in which to make his name. "In atomic physics, we still have a wealth of uninterpreted experimental results," he told Heisenberg. "Nature's evidence in one place seems to contradict that in another, and so far it has not been possible to draw an even halfway coherent picture of the relationship involved." It was likely, thought Pauli, that everyone would still be groping about in a thick mist for years to come. As Heisenberg listened, he was inexorably drawn into the realm of the quantum. Sommerfeld soon assigned Heisenberg a little problem in atomic physics. He asked him to analyze some new data on the splitting of spectral lines in the magnetic field and to construct a formula that replicated the splitting. Pauli warned Heisenberg that Sommerfeld hoped that deciphering such data would lead to new laws. It was an attitude that for Pauli bordered on a kind of number mysticism, but then he admitted, "No one has been able to suggest anything better." The exclusion principle and electron spin still lay in the future. Heisenberg's ignorance of the accepted rules and regulations of quantum physics allowed him to tread where others, wedded to a more cautious and rational approach, feared to. It enabled him to construct a theory that appeared to explain the anomalous Zeeman effect. Having dismissed an earlier version, Heisenberg was relieved when Sommerfeld sanctioned the publication of his latest effort. Although it was later shown to be incorrect, his first scientific paper brought Heisenberg to the attention of Europe's leading physicists. Bohr was one of those who sat up and took notice. They first met in Göttingen in June 1922, when Sommerfeld took some of his students to hear Bohr's series of lectures on atomic physics. What struck Heisenberg was how precise Bohr was in his choice of words. Each one of his carefully formulated sentences revealed a long chain of underlying thoughts, of philosophical reflections, hinted at but never fully expressed. He was not alone in sensing that Bohr reached his conclusions more by intuition and inspiration rather than detailed calculations. At the end of his third lecture, Heisenberg rose to point out some difficulties that remained in the published paper that Bohr had praised. As people began to mingle after the question and answer session, Bohr sought out Heisenberg and asked the 20-year-old if he would like to accompany him on a walk later that day. Their hike to a nearby mountain lasted some 3 hours, and Heisenberg later wrote that my real scientific career only started that afternoon. For the first time, he saw that one of the founders of quantum theory was deeply worried by its difficulties. When Bohr invited him to Copenhagen for a term, Heisenberg suddenly saw his future as one full of hope and new possibilities. Copenhagen would have to wait. Sommerfeld was due to go to America, and in his absence had arranged for Heisenberg to study with Max Born in Göttingen. Although he looked like a simple farm boy with short fair hair, clear bright eyes, and a charming expression, Born quickly discovered that there was much more to him than met the eye. He was easily as gifted as Pauli, Born wrote to Einstein. When he returned to Munich, Heisenberg finished his doctoral thesis on turbulence, and Sommerfeld had chosen the topic to broaden his knowledge and understanding of physics. During the oral examination, his inability to answer simple questions, such as the resolving power of a telescope, almost cost him his doctorate. Wilhelm Wien, the head of experimental physics, was dismayed when Heisenberg struggled to explain how a battery worked. He wanted to fail the upstart theorist, but reached a compromise with Sommerfeld. Heisenberg would get his doctorate, but would be awarded the second lowest mark, grade 3. Heisenberg had passed with grade 1. Feeling humiliated, that evening he packed his bags and caught the overnight train. He could not bear to stay in Munich a minute longer and fled to Göttingen. I was astonished when, one morning long before the appointed time, he suddenly appeared before me with an expression of embarrassment on his face, recalled Born later. Heisenberg anxiously recounted the tale of his oral examination. The tale of his oral exam, worried that his services would no longer be required as an assistant. Eager to cement Göttingen's growing reputation for theoretical physics, Born was confident that Heisenberg would bounce back, and told him so. Born was convinced that physics had to be rebuilt from the ground up. The mishmash of quantum rules and classical physics was at the heart of the Bohr-Sommerfeld quantum atom, had to give way to a logically consistent new theory that Bohr called quantum mechanics. None of this was new for physics trying to disentangle the problems of atomic theory. However, it signaled the awareness of a creeping sense of crisis in 1923 at the inability of physicists to cross the atomic Rubicon. Pauli was already loudly proclaiming to anyone who would listen that the failure to explain the anomalous Zeeman effect was evidence that we must create something fundamentally new. After meeting him, Heisenberg believed that Bohr was the one most likely to make the breakthrough. Pauli had been in Copenhagen as Bohr's assistant since the autumn of 1922. He and Heisenberg kept each other informed about the latest developments at their respective institutes throughout a regular exchange of letters. Heisenberg, like Pauli, had also been working on the anomalous Zeeman effect. Just before Christmas of 1923, he wrote to Bohr about his latest efforts and received an invitation to spend a few weeks in Copenhagen. On Saturday, 15th of March 1924, Heisenberg stood in front of the three-story neoclassical building with its red-tiled roof at Blegdomsjev 17. Above the main entrance, he saw the sign that greeted every visitor: Universitets Institut for Theorische Physik, better known as the Bohr Institute. Heisenberg soon discovered that only half the building, the basement and the ground floor, was used for physics. The rest was set aside for accommodation. Bohr and his growing family lived in an elegantly furnished flat that occupied the entire first floor. The family maid, the caretaker, and honored guests were housed at the top floor. On the ground floor, besides the lecture hall with its 6 long rows of wooden benches, was a well-stocked library and offices for Bohr and his assistant. There was also a modest-sized workroom for visitors. Despite its name, the institute had 2 small laboratories on the first floor, with the main laboratory housed in the basement. The institute was struggling for space with a permanent staff of 6 and almost a dozen visitors. Bohr was already making plans to expand. Over the next 2 years, the adjacent land was bought and 2 new buildings were added that doubled the capacity of the institute. Bohr and his family moved out of their flat into a large purpose-built house next door. The extension meant a substantial renovation of the old building that included more office space, a dining room, and a new self-contained 3-room flat on the top floor. It was here that Pauli and Heisenberg often stayed in later years. Let me just see. Okay. There's one thing that no one at the institute wanted to miss: the arrival of the Morning Post. Letters from parents and friends were always welcome, but it was correspondence from far-flung colleagues and the journals that were seized upon for the latest breaking news from the frontiers of physics. However, not everything revolved around physics, even if much of the talking did. There were musical evenings, games of table tennis, hiking trips, and outings to watch the latest motion picture. Heisenberg had arrived with such high hopes, but his first few days at the institute left him feeling frustrated. Expecting to spend time with Bohr almost as he stepped through the front door, he had hardly seen him. Used to being the best, Heisenberg was suddenly faced with Bohr's international posse of brilliant young physicists. He was intimidated. They all spoke several languages, while he sometimes struggled to express himself clearly in German. What irony. Enjoying nothing more than walks in the countryside with his friends, Heisenberg thought that everyone at the institute possessed a worldliness that he did not. However, nothing left him as despondent as the realization that they understood more of atomic physics than he did. As he tried to shake off the blows to his self-esteem, Heisenberg wondered if he would ever get the chance to work with Bohr. He had been sitting in his room when there was a knock on the door, and in strode Bohr. After apologizing for being so busy, he proposed that 2 of them go on a short walking tour. There was little chance, Bohr explained, of him being left alone long enough at the institute for the pair of them to talk at any length. What better way of getting to know one another than a few days of walking and talking? It was Bohr's favorite pastime. Early in the morning, they caught the tram to the northern outskirts of the city and began their walk. Bohr asked Heisenberg about his childhood and what he remembered about the outbreak of war 10 years earlier. Sorry. Just painful burps. Full of pain. As they headed north, instead of physics, they talked about the pros and cons of war, Heisenberg's involvement in the youth movement, and Germany. After spending the night at an inn, they walked to Bohr's country cottage in Tisvelde before heading back to the institute on the 3rd day. That 100-mile walk had the effect that Bohr desired and Heisenberg craved. They got to know each other more quickly. They had talked about atomic physics, yet when they finally returned to Copenhagen, It was Bohr the man, rather than the physicist, that had captivated Heisenberg. I am, of course, absolutely enchanted with the days I am spending here, he wrote to Pauli. He had never before met a man like Bohr with whom he could discuss just about anything. Despite his genuine concern for the welfare of everyone at his institute, Sommerfeld upheld the traditional German role of professor, one step removed from his subordinates. In Göttingen, Heisenberg would not have dared to broach with Born the range of subjects that he and Bohr had discussed so freely. Unknown to him, it was Pauli, in whose footsteps he always seemed to be following, who was behind Bohr's warm reception. Pauli always took a keen interest in what Heisenberg was doing, as the pair kept each other informed about their latest ideas. Bohr had returned to Hamburg University when he learned that Heisenberg was going to spend a few weeks in Copenhagen, and he wrote to Bohr. For a man already notorious for his scathing wit, the fact that he described Heisenberg as a gifted genius who would one day advance science greatly made a deep impression on Bohr. But before that day arrived, Pauli was sure that Heisenberg's physics had to be underpinned by a more coherent philosophical approach. Pauli believed that to overcome the problems besetting atomic physics, it was necessary to stop making arbitrary and ad hoc assumptions whenever experiments yielded data in conflict with existing theory. Such an approach could only paper over the problems without ever leading to their solution. Given his deep understanding of relativity, Pauli was an ardent admirer of Einstein and the way in which he had constructed a theory using a few guiding principles and assumptions. Believing that it was the correct approach to adopt in atomic physics too, Pauli wanted to emulate Einstein by setting up the underlying philosophical and physical principles before moving on to develop the necessary formal mathematical nuts and bolts that held the theory together. By 1923, it was an approach that had left Pauli in despair. Having avoided introducing assumptions that could not be justified, he nevertheless failed to find a consistent and logical account of the anomalous Zeeman effect. Hopefully you will then take atomic theory forward in good measure and solve several of the problems with which I have tormented myself in vain and which are too difficult for me, Pauli wrote to Bohr. I hope also that Heisenberg will then bring back home a philosophical attitude in his thinking. By the time the young German arrived, Bohr had been well briefed. Throughout the 2-week visit, the principles of physics rather than any particular problem was the focus of their discussions as Bohr and Heisenberg strolled through Feild Park next to the Institute, or chatted over a bottle of wine in the evenings. Many years later, Heisenberg described his time in Copenhagen in March 1924 as a gift from heaven. I shall, of course, miss him. He is a charming, worthy, very bright man who has become very dear to my heart, but his interest precedes mine, and your wish is decisive for me, Born wrote to Bohr after Heisenberg received an invitation for an extended stay in Copenhagen. Due to spend the forthcoming winter semester teaching in America, Bohr would not need the services of his assistant until May the following year. At the end of July 1924, having successfully completed his habilitation thesis and gained the right to teach at German universities, Heisenberg left for a three-week hiking tour around Bavaria. When he returned to Bohr's Institute on 17th of September 1924, Heisenberg was only 22 years old, but had already written or co-written an impressive dozen papers on quantum physics. He still had much to learn, and knew that Bohr was the man to teach him. From Sommerfeld, I learned optimism. In Göttingen, mathematics. From Bohr, physics, he said later. For the next 7 months, Heisenberg was exposed to Bohr's approach to overcoming the problems that plague quantum theory. While Sommerfeld and Born were also troubled by the same inconsistencies and difficulties, neither man was haunted like Bohr by them. He could hardly bring himself to talk of anything else. From these intense discussions, Heisenberg realized how difficult it was to reconcile the results of one experiment with those of another. Among these experiments was Compton's scattering of X-rays by electrons that supported Einstein's light quantum. The difficulties just seemed to multiply with de Broglie's extension of wave-particle duality to encompass all matter. Bohr, having taught Heisenberg all that he could, had great hopes for his young protege. Now everything is in Heisenberg's hands to find a way out of the difficulties. By the end of April 1925, Heisenberg was back in Göttingen, thanking Bohr for his hospitality and sad about the fact that I must carry on wretchedly alone by myself in the future. Nevertheless, he had learned a valuable lesson from discussions with Bohr and in his ongoing dialogue with Pauli. Something fundamental had to give. Heisenberg believed he knew what that might be as he tried to solve a long-standing problem: the intensities of the spectral lines of hydrogen. The Bohr-Sommerfeld quantum atom could account for the frequency of hydrogen spectral lines, but not how bright or dim they were. Heisenberg's idea was to separate what was observable and what was not. The orbit of an electron around the nucleus of a hydrogen atom was not observable, so Heisenberg decided to abandon the idea of electrons orbiting the nucleus of an atom. It was a bold step, but one he was now ready to take, having long detested attempts at pictorial representations of the unobservable. As a teenager in Munich, Heisenberg was enthralled by the idea that the smallest particles of matter might reduce to some mathematical form. At about the same time, he came across an illustration in one of his textbooks that he found appalling. To explain how one atom of carbon and two atoms of oxygen formed a carbon dioxide molecule, the atoms were drawn with hooks and eyes by which they could hang together. Heisenberg found the idea of orbiting electrons inside the quantum atom similarly far-fetched. He now abandoned any attempt to visualize what was going on inside an atom. Anything that was unobservable he decided to ignore, focusing his attention only on those quantities that could be measured in the laboratory, the frequencies and intensities of the spectral lines associated with light emitted or absorbed as an electron jumped from one energy level to another. Even before Heisenberg adopted this new strategy, Pauli had already expressed his doubts about the usefulness of electron orbits more than a year earlier. The most important question seems to me to be this: to what extent may definite orbits of electrons in stationary states be spoken of at all? He had written in italics to Bohr in February 1924. Even though he was well on the road that led to the exclusion principle, and concerned about the closure of electron shells, Pauli nevertheless answered his own question in another letter to Bohr in December. We must not bind atoms in the chains of our prejudices, to which, in my opinion, also belongs the assumption that electron orbits exist in the sense of ordinary mechanics, but we must, on the contrary, adapt our concepts to experience. They had to stop making compromises and cease trying to accommodate quantum concepts within the comfortable and familiar framework of classical physics. Physicists had to break free. The first to do so was Heisenberg when he pragmatically adopted the positivist credo that science should be based on observable facts and attempted to construct a theory based solely on the observable quantities. And fucking hell, finally there's a break. I feel like at the end I was just going, just trying to survive, man. Shit's too long. I was also probably rushing. I was probably rushing. I'm taking a break right now. Oh man. Alright, we've got 12 more pages. Cool. And there's only 8 more pages to the next break. Okay, let's do this, y'all. Let's finish this. In June 1925, a little more than a month after returning from Copenhagen, Heisenberg was miserable in Göttingen. He was struggling to make headway in calculating the intensities of the spectral lines of hydrogen, admitted as much in a letter to his parents. He complained that everyone here is doing something different and no one anything worthwhile. A very severe attack of hay fever contributed to his low spirits. I couldn't see from my eyes. I was just in a terrible state, Heisenberg said later. Unable to cope, he had to get away, and a sympathetic board granted him a 2-week holiday. On Sunday, the 7th of June, Heisenberg caught the night train to the port of Cuxhaven on the coast. Arriving early in the morning, tired and hungry, Heisenberg went in search of breakfast at an inn and then boarded a ferry to the island of Helgoland, an isolated barren rock in the North Sea. Originally owned by the British until it was traded for Zanzibar in 1890, Helgoland was 30 miles from the German mainland and less than a square mile in size. It was here that Heisenberg hoped to find relief amidst the bracking amidst the bracing, pollen-free sea air. On my arrival, I must have looked quite a sight with my swollen face. In any case, my landlady took one look at me, concluded I had been in a fight, and promised to nurse me through the after effects, Heisenberg recalled when he was 70. The guest house was high on the southern edge of the distinctive island, carved out of red sandstone rock. From the balcony of his second floor, Heisenberg had a wonderful view of the village below, the beach, and the dark brooding sea beyond. In the days that followed, he had time to think about Bohr's remark that part of infinity seems to lie within the grasp of those who look across the sea. It was in such reflective mood that he relaxed by reading Goethe, taking daily walks around the small resort, and swimming. Soon he was feeling much better. With little to distract him, Heisenberg's thoughts turned once more to problems of atomic physics, but here on Helgoland he felt none of the anxiety that had recently plagued him. Relaxed and carefree, he quickly jettisoned the mathematical ballast he had brought from Göttingen as he tried to solve the riddle of the intensities of the spectral lines. In his quest for a new mechanics of the quantized world of the atom, Heisenberg concentrated on the frequencies and relative intensities of the spectral lines produced when an electron instantaneously jumped from one energy level to another. He had no other choice. It was the only available data about what was happening inside an atom. Despite the imaginary conjured up by all the talk of quantum jumps and leaps, an electron did not jump through space as it moved between energy levels, like a boy jumping off a wall onto the pavement below. It was simply in one place, and an instant later, it popped up in another without being anywhere in between. Heisenberg accepted that all observables, or anything connected with them, were associated with the mystery and magic of the quantum jump of an electron between two energy levels. Lost forever was the picturesque miniature solar system, in which each electron orbited a nuclear sun. On the pollen-free haven of Helgoland, Heisenberg devised a method of bookkeeping to track all possible electron jumps, or transitions, that could occur between the different energy levels of hydrogen. The only way he could think of recording such observable quantities, each associated with the unique pair of energy levels, was to use an array. And this is just V11, V12, V13, V14, V1n, V21, V22, V23, V24, V2n, and so on. This was the array for the entire set of possible frequencies for the spectral lines that could theoretically be emitted by an electron when it jumps between two energy levels. If an electron jumps from the energy level E2 to the lower energy level E1, a spectral line is emitted with a frequency designated by V21 in the array. The spectral line of frequency V12 would only be found in the absorption spectrum, since it is associated with an electron in energy level E1 absorbing a quantum of energy sufficient to jump to energy level E2. A spectral line of frequency Vmn would be emitted when an electron jumps between any two levels whose energies are Em and En, where m is greater than n. Not all the frequencies Vmn are exactly observed. For example, measurement of V11 is impossible since it would be the frequency of the spectral line emitted in a transition from energy level E1 to energy level E1 of physical impossibility. Hence, if V11 is 0, as are all potential frequencies when m is equal to n. The collection of all non-zero frequencies Vmn would be the lines actually present in the emission spectrum of a particular element. Another array could be formed from the calculation of transition rates between the energy levels. If the probability of a particular transition Amn from energy level Em to En is high, then the transition is more likely than one with a lower probability. Resulting spectral line with frequency Vmn would be more intense than for the less probable transition. Heisenberg realized that the transition probabilities Amn and the frequencies Vmn could, after some deft theoretical manipulation, lead to a quantum counterpart for each observable quantity known in Newtonian mechanics, such as position and momentum. Of all things, Heisenberg began by thinking about electrons' orbits